We would like to welcome you and thank you for joining us for this installment of the Groundwater Foundation's webinar series, co-sponsored by the Water Research Foundation. In order to achieve the Groundwater Foundation's mission, the Foundation is offering webinars. This is our first one for 2010, and while we'll continue to offer some conferences, seminars, and workshops, we feel the webinar series offers us the opportunity to provide valuable resources to all of you on a minimal cost and no travel expenses. My name is Brian Reitz. I'm a program coordinator at the Groundwater Foundation here in Lincoln, Nebraska, and I'll be hosting today's Groundwater Foundation webinar, Quantifying the Groundwater Reserves of the United States, Current Conditions, Trends, and Sustainability. I just wanted to walk you through one feature that we'll be using during the course of today's event. It's the chat feature. If you would like to ask questions of me or the presenter during the course of the webinar, please type your question into the chat box just to the left of the send button in the bottom right-hand section of your computer. I will monitor the questions throughout the presentation, and then we'll address as many of them as possible during the Q&A segment at the end. Today's topic is Quantifying the Groundwater Reserves of the United States, Current Conditions, Trends, and Sustainability with Kevin Dennehy. Kevin is the coordinator for the USGS Groundwater Resources Program in Reston, Virginia. The Groundwater Resources Program focuses on national and regional interests in groundwater by conducting multidisciplinary large-scale studies of groundwater availability, developing new field techniques, geophysical methods, and computer models to monitor and analyze groundwater systems, and monitors changes to groundwater conditions resulting from climate variability and withdrawals. He has more than 30 years of experience in the study and analysis of all aspects of hydrology and is the author or co-author of more than 50 publications on topics like surface water and groundwater interactions, unsaturated zone processes, surface water and groundwater simulation, surface water and groundwater quality sampling, and analysis, and aquifer test analysis. And he received undergraduate and graduate degrees from the University of New Hampshire and the University of South Carolina. So welcome, Kevin.
Okay, thank you, Brian. Hopefully everyone can hear me fine. Again, good afternoon and welcome. As Brian said, my name is Kevin Dennehy, and the title of my presentation is shown on the screen. Okay. I'd like to start by going over a presentation outline, tell you what I'm going to be talking about today. I'm going to start off with talking about the importance of groundwater as a natural resources, trying to give you some context and perspective before we get into details related to groundwater availability. Going to then go into a couple definitions so we're all at the same place, and then go over what we know about groundwater reserves in the United States. Then I wanted to talk about what we're currently doing in the USGS to improve our knowledge of current conditions and trends in groundwater availability. And then I'll have a few closing comments on groundwater sustainability. Well, this is an image of the water cycle, which we're all familiar with. Groundwater is often overlooked and is often undervalued part of the hydrologic cycle. Groundwater serves as a vast subsurface reservoir and is a key to the interaction between surface water and groundwater. I'd like to start out by looking at the big picture for context and perspective. This box, you see the blue box, represents the total amount of water on the planet. About 97% of the water on the planet is in its oceans. That leaves 3% of the water remaining as fresh water on the rest of the Earth. Let's break down that fresh water component a little more. About 69% of the fresh water is locked up in ice caps, glaciers, and saline seas. That amount is pretty much unavailable for supply or human use. Of the available fresh water remaining, 96% of that is groundwater. About 1% is surface water. In the U.S. and around the world, much effort has been spent on defining and quantifying surface water resources. With those resources pretty much spoken for, I suggest it might be prudent to spend more effort to quantify and assess the groundwater resources, especially in the United States. Groundwater is important to us because it is a source of drinking water for at least 50% of the population in the U.S., about 98% of the water used for rural domestic supplies, and about a third of the water used for public supplies. About 40% of water used for irrigation is groundwater, and it sustains flow in most streams and rivers in the United States and elsewhere. It also, groundwater, maintains a variety of aquatic ecosystems. Let's talk about trends in water use in the U.S. The USGS since 1950 has been doing every 5 years a compilation of water use for the nation. The total water use withdrawals have more than doubled between 1950 and 2005. During the same period, the groundwater and surface water supply has expanded as population has expanded. And you can see there, the orange indicates the population growth with time, and the blue bars are the withdrawals for total water use with time. This next image shows water withdrawals broken down by category for 2005. Total fresh and saline withdrawals for surface water and groundwater were 410 billion gallons per day for 2005. Thermoelectric and irrigation accounted for 80% of total withdrawals, or 329 billion gallons per day. Water use for public supply is expanding along with population. Public supply is a component of the water-energy nexus and likely to also expand in light of increasing energy demands. Now let's do a breakdown of the surface water and groundwater part of the total water use. The blue bar indicates surface water. The light blue is groundwater. This graph shows groundwater provides most of the water for livestock, mining, and domestic supply in the U.S. Nearly all the water for residential and domestic use is from groundwater, while nearly all of the water for thermoelectric cooling is surface water. The bar in the middle of this image shows the comparison of the categories of use, including thermoelectric power for all water use categories. It's just another way of representing what we just saw. The bar on the far right shows the comparison of use excluding thermoelectric power. Excluding thermoelectric power, irrigation is 62% of the total, and public water of the total water use, and public supply becomes 22% of the total. As I just indicated, the thermoelectric, most of that is from surface water, so there's much more dependency on groundwater in that second bar on the far right. The second largest water use, the total water use, And the first, if we exclude thermoelectric, is irrigation. As I mentioned, 42% of the irrigation withdrawals is from groundwater. The majority of irrigation withdrawals, about 85%, and irrigated acres, about 74% of the total, were in the 17 western states. Nearly 90% of the groundwater used for irrigation was withdrawn in 13 states. If you look at the graphics, by 1980, the quantity of groundwater had nearly doubled because of expansion of irrigation in areas of the central U.S. to 40% of the irrigation total. So even though there's been a leveling off of water use for irrigation in the West, there's been an increase that's particularly apparent since 1980 in the East for groundwater. So let's look at public supply withdrawals. Public supply has continued to increase along with population. It's the third largest water use of all water use categories. Groundwater has generally accounted for about a third of the water withdrawals for public supply. About 86% of the U.S. population obtains their drinking water from public suppliers. In 2005, the remaining approximately 43 million people, or 14% of the population, were self-supplied, and as I mentioned previously, that's predominantly from groundwater supplies. Okay, I've spent some time talking about and setting the table for how important groundwater is to both the world and the nation. Now I'd like to talk about some of the challenges facing the U.S. with respect to groundwater resources or its reserves. There are increasing demands on that resources from increasing populations. There are challenges to be faced from competition between surface water and groundwater uses, and there's challenges related to water quality requirements. Certain uses require certain water quality. There is also a growing realization that ecological needs have a place at the table, and there are challenges making sure that that water is available. And I would contend that in the future we're going to see even greater demands from economic changes related to agriculture, urbanization, and energy on the available surface and groundwater resources. Well, although all these challenges are real, I would say they're not insurmountable. This awareness of these challenges leads to some basic questions about the resources and the groundwater reserves. How much groundwater do we have? Are we running out? Where are groundwater resources most stressed? And where are resources most available for future human use? Although these questions seem rather simple, providing answers becomes a little more complex. Before we go on, I'd like to go ahead and define a couple terms so again we're starting from the same place. Let's talk about water availability. Well, we recognize that water availability is a function of many factors. It is not only the quantity that determines availability. Other important considerations such as water quality, the physical structure, laws, regulation, and social economic factors control its demand and use. The USGS efforts through the groundwater availability studies will focus on quantifying the physical characteristics that are important indicators of groundwater availability. I would contend prior to determining availability, one needs to quantify the resources, and that's what the USGS intends to do. However, that's what we're trying to do on a national scale, but on a local scale, these characteristics must be considered jointly with societal factors as determinants of actual groundwater availability. Society's tolerance for the consequences of its use has to do with what water would be available. And an aspect of it that we'll revisit is societal perspectives and constraints change with time, just as groundwater resources change. Well, I'd like to talk about definition of groundwater reserves. And it's being used here to emphasize the fact that groundwater, like other natural resources, can be depleted. So I'm talking about reserves from a depletion standpoint. This map shows changes in saturated thickness as a percent of pre-development saturated thickness for the High Plains aquifer. The red areas on the right in Texas, where there are more than 50% decline in saturated thickness. This system will not recover in our lifetimes and is adversely impacted the economy of those areas. So in this particular instance, you could look at that as groundwater has been mined or that reserve has been depleted. And that's how I intend to use the term and refer to it through the remainder of this presentation. Groundwater is renewable. However, in this particular case, in a semi-arid or arid area, it will not be in the time. There's a time lag problem with regard to renewing that resource. Okay, moving on to the next part of the presentation. What do we know about the nation's groundwater reserves? Well, over the years, the USGS has conducted several national assessments of the nation's groundwater resources. Actually, efforts started by Meisner in about 1923 republished the occurrence of groundwater in the U.S. Since that time, there has been subsequent publications of various aspects of looking at the national perspective related to groundwater. The latest publication for a national assessment of the regional aquifer systems analysis studies that were conducted between 78 and 92. And these were the first time that these aquifers were looked in detail at the amount of water that was available. Well, given all this information and what the USGS has developed on a national basis, don't we know enough about the groundwater availability? And I would contend there's more to learn. Nationally, we have a basic qualitative description of groundwater resources. However, at a smaller scale, regional, sub-regional, and local scales, more work is needed. And there's also an aspect of a temporal variability that must be explored. This is an image of an updated qualitative representation of groundwater depletion showing areas of groundwater level declines in the U.S. This image was put together for a recent report released in reference there in 2008. But the point I want to make here is that depending on the location, whether it's a blue dot or a pink dot, meaning declines in excess of certain amounts, this is put in by talking to people and looking at information in databases. This is not an exhaustive study. In order to manage your water for the use and to respond to the questions that I posed earlier, we need more of a quantitative assessment of groundwater availability. This is an image of a report cover of a report released in 2008, Groundwater Availability in the United States, which examines what is known about the nation's groundwater availability and outlines a strategy for future national and regional studies that would provide information to help state and local agencies make informed water availability decisions. Well, as we know, the groundwater doesn't reside in the subsurface as a vast pool of water that we can tap at any time. The USGS has mapped the 65 principal aquifers across the U.S. and are illustrated on this map. This is a 2D representation, and actually we know that aquifers are mapped in 3 dimensions. The location of aquifers are fundamental to determination of groundwater availability. This principal aquifer map provides a broad understanding of where water-bearing formations are in the U.S. and provides a framework to classify and study regional groundwater systems. So these units, these principal aquifers, will be our units of measure to assessing groundwater availability nationally. Well, I know I talked about water use and I gave you a lot of statistics previously, but it is important enough that I want to go over one more time. The 2 basic types of information that is needed to assess groundwater availability is 1, supply, and 2, demand. I just mentioned about the supply, knowing where the groundwater is in these aquifer units, and the other is the demand. Well, nationally, we are able to estimate relative rankings as shown on this image, but on a regional, sub-regional, and local scale, much more work is needed to understand how that demand affects supply. So how water use is used would be important to knowing its availability. Well, I want to talk about the regional groundwater availability studies that the USGS through the Groundwater Resources Program is currently conducting, and start out by talking about the objectives of those studies. There are threefold. We want to quantify the current groundwater resources in the units as I described. We want to evaluate how these resources have changed over time. And we want to provide tools to forecast system responses to stresses from future human and environmental uses. These objectives will enable us to address questions that I raised earlier in the presentation. Those questions were, how much water do we have, how much do we need, and where are the remaining resources or reserves? Moreover, this assessment is structured to provide a national perspective on the nation's groundwater resources, while simultaneously emphasizing the value of the regional assessments to those who manage and use the resources, both regionally and locally. I want to take a minute or two to talk about the study design itself. I want to make it clear that these studies will build on the foundation of previous existing information. That's information provided and collected not only by the feds through the USGS and other federal agencies, but also state, local agencies and organizations that have information related to groundwater availability, information on supply and demand. These studies will be large in scope and multidisciplinary in nature. These studies will share common national objectives, and the studies, although are nationally directed, but they will need to be regionally affected because the residents of those areas, of those aquifer systems, understand the availability questions, issues that need to be addressed. This is a map showing the current locations where groundwater availability studies have or are taking place. A single study takes about 4 years to complete, and we're only able to start one new study per year. So it's going to take a little while to do those aquifers nationally. The approach outlined in that report I showed earlier is designated to provide useful regional information for state and local agencies who manage groundwater resources, while also providing the building blocks for a national assessment. So as we acquire information on an aquifer unit, we will then build on each of those studies until we cover the aquifers across the nation. This report places the regional studies by the USGS, the ones I'm describing, as a long-term effort to understand groundwater availability nationally. The report identifies 30 regionally priority aquifers to be included in that national assessment. This set of principal aquifers was primarily selected on the basis of water use. These 30 aquifers account for 94% of the total groundwater use in the U.S. Okay, I told you about the study. Now I want to go over, so what are sort of some of the products or outcomes from these studies, and how do we get to knowing a little bit more about water availability? Well, I've listed those products here. We will develop water budgets for major aquifer systems. We will gain information about the trends in groundwater use of these systems, the storage, recharge, and discharge. We will develop groundwater models that will provide a context where we can go ahead and look at more local scale concerns and issues. And these groundwater models are actually tools which we'll use to make further projections of groundwater availability or sustainability. We will also acquire information on the region-wide estimates of key hydrologic variables. We'll assess climate variability effects on future groundwater availability. And with these tools we'll develop, we'll use those to evaluate existing networks for monitoring. Okay, I've kind of listed those here, but I'd like to show you what those might look like, those products. So the next several slides, we'll take a look. Well, this is an image of the Mississippi Embayment principal aquifer. As part of doing these investigations, we need to establish what the subsurface looks like and gain insights into the hydrologic properties of these deposits. We'll use geophysical logs, core from the subsurface, and cuttings to formulate our understanding of these subsurface materials. I had an animation on this to show you what that subsurface might look like, and unfortunately I'm unable to get that to work. But that information is integrated here so we can have a picture of what the subsurface might look like. Well, I'd like to talk about water budgets. And water budgets can be used as a tool to understand water resources of a system. When you're estimating the volume of water stored in aquifers, that's a little more difficult than estimating the volume of water in streams or rivers, clearly, I think. Each groundwater system is unique in its source and volume of water flowing through that system, and those systems are dependent upon the external factors such as the rates of precipitation, recharge, evaporation, and ET. Basin-wide water budgets are needed to properly manage groundwater resources. And what you see here on the top is a groundwater system in equilibrium. What that means is that water coming into that system, the blue area, the aquifer storage, recharge, water coming in is equal to water going out, discharge. So that system is then in equilibrium. Well, in the bottom graphic, you see that the groundwater system is being pumped. Water is being removed from that system. Now that system is no longer in equilibrium. That the only way the system actually tries to seek equilibrium, the only way it can do that is it has to increase recharge or decrease discharge to come to that new equilibrium. If it's unable to do that, we have a change in the aquifer storage. Well, here's an example of a water budget, a groundwater budget for the total system of California's Central Valley. The units, you can see the numbers are in millions of acre-feet per year. On the left, you have the pre-development water budget, and on the right, you have the post-development water budget. Water development for irrigation has had a pronounced effect on the hydrologic budget of the California Central Valley, and I think that's clear from these images. Development of surface water and groundwater in support of agriculture has fundamentally altered the recharge and discharge components of the valley's groundwater budget. Prior to development, on the left, the groundwater system is in equilibrium or near equilibrium. That means water coming into the system is equal to water going out of the system, and there's no loss of storage. In post-development, that's after human intervention or pumping, the ag and urban development has drastically altered the groundwater budget in the Central Valley. Water demand is being met by a combination of groundwater withdrawals, you can see that groundwater pumping, and surface water imports. I hope it is clear that this type of analysis is fundamental to assessing the system's groundwater availability. These findings will provide the foundational information and modeling tools to help state and local agencies make water availability decisions based on local water management constraints and goals. This next slide illustrates the variety of ways in which overall groundwater budgets can change in response to large-scale pumping. These circles represent the distribution of various water budgets, meaning discharge and recharge and storage changes. The red color indicates a decrease in storage. And I think what most people would think, because of pumping, you'll think that most systems react in their water budgets when they go out of equilibrium as a decrease in storage. But as you can see from this image, there are very large blues and yellows, meaning in some systems, water is taken or captured from discharge or surface water resources, and in others, recharge increased to make up the water that is being lost through pumping. The major point I want to make here is that each system is unique, and we need to perform quantitative analysis to understand the dynamics of each system so we can be able to come to grips of what water might be available. Well, I want to explain this slide, and bear with me on this. Here you can see this is the cumulative change in storage for the work we did in the Central Valley, California. Each of these different colored lines represent a sort of a basin within the Central Valley. The dark blue diamonds, the dark blue line, indicates sort of the total of all those different pieces. So there are 4 different basins, and the blue line indicates the sum total of those. What you see here is that the California Central Valley simulation has showed that the cumulative change in storage has reached a maximum of loss of 47.5 million acre-feet in the mid-90s and has recovered slightly since then. This graph enables us to see how the return of a relatively wet climate, now I want to draw your attention to the year about 1993. You can see that blue line reaches a low there, and you can see in the background is that blue color. That is a wet period in that basin, and because of that coming wet period and the fact that the climate was wetter, the surface water deliveries to that the Central Valley increased because of the wetter period, and because of those increased surface water, groundwater pumpage decreased. Water began to recharge the system and gain or reduce the amount of loss that you saw in the system. Following these trends in groundwater availability provides the ability for wise management of these groundwater reserves and resources. So this image allows us to look at the effects of humans on the storage and the available groundwater, and also the effects of climate on that resource. This was another animation. Unfortunately, it's not working. But this is the results of a groundwater modeling that basically shows drawdowns with time as you would turn on the pumping. The pumping began for the Mississippi Embayment area in 1870, and we show how water withdrawals over that time affects the water table in that system up to the year 2000. Now, the tools we develop and calibrate with this information allows us then to forecast or look at various scenarios of how climate and or planned water use might affect the system as we look forward. And that would help us try to get a handle on sustainability and how long groundwater supplies might be available in certain areas and where there are areas where there could be other supplies worth exploration. Well, I've been talking for a little while now, and I'd like to sort of give you some of my final comments regarding sustainability and groundwater sustainability in particular. I've provided a definition here taken from Alley and Lee in 2004 paper in Groundwater. The definition is groundwater sustainability is defined as development and use of groundwater resources in a manner that can be maintained for an indefinite amount of time without causing unacceptable environmental, economic, and social consequences. Well, it's a mouthful, but it's also difficult to achieve. The sustainability of groundwater resources is a function of many factors. Some real-world examples of how sustainability might be affected is we could have, because of withdrawals or use, decrease in groundwater storage, as I've shown, reduction in stream flow, the capture of water that were on its way to streams, capture of water going to lakes, or reduction in spring discharges. We could have a loss of wetlands and riparian ecosystems. We could have land subsidence, saltwater intrusion, and changes in groundwater quality. Any and all of these might be possible on your definition of what is acceptable. So if any of those items might be acceptable, you might have available resources. Clearly, sustainability is a subjective term, and it's very much in the eye of the beholder. Each groundwater system and development situation is unique and requires an analysis evaluating all possible factors before we can make a determination about availability. Decisions made will need to be revisited because social, economic, and legal constraints can change over time, and what is available today, it might become unavailable or available in the future. It's a bit of a moving target, and that's why a constant iterative or analysis situation needs to occur, especially in stressed areas. A key challenge for sustained use of groundwater resources is to frame the hydrologic implications of various alternative development strategies in such a way that their long-term implications can be properly evaluated. With groundwater withdrawals, there is oftentimes a time lag associated with those impacts. So water can be withdrawn from a system that perhaps was on its way to be discharged to a surface water body like a river, and that could be intercepted, but you might not see the effect of that for many years after that. So it's very important to, when you do an analysis of availability, that you take both short and long-term factors into consideration. Okay, this is near my final slide. I just want to go over some of my take-home messages here. I think I've shown, I hope I have, that groundwater is one of the U.S.'s most important natural resources and is essential to the nation's health and future economic well-being. Groundwater and surface water is a single resource. Understanding interactions is fundamental to the development of effective groundwater resource management and policy. And I guess this is the bumper sticker statement that I would leave you with, is that you can't effectively manage what you don't measure or understand. The nation's groundwater resources should be assessed at a scale of principal aquifers and be representative of a variety of conditions and provide a national perspective on all types of groundwater systems. Finally, a holistic systems approach is needed to evaluate groundwater sustainability in both the short and long term and at scales that make sense from a hydrologic standpoint. As I stated here, I contend that those are principal aquifer scale. Societal factors will need to be considered in all decision making regarding groundwater availability and sustainability. And this is my final slide, and we're in the process of doing these studies and developing more knowledge related to availability. And here's our website with the address shown. If you want to track our progress, you can do that from the website, and my contact information is shown here. And I thank you for listening.
All right, thanks, Kevin. Now's the time for some questions. I received some during your presentation. If you have more questions, just a reminder to type them into the chat feature in the bottom right-hand corner of your screen on most people's screens. One of the questions Kevin asked, how does the USGS calculate water use nationwide, and maybe what documents and reports are mined for this data?
As I mentioned, I think in the presentation, was that every 5 years there's a national compilation of water use. That includes surface water, groundwater, and saline resources. And in our offices, we have a distributed office in the field, and those people contact water purveyors and providers and get information related to use. And every 5 years, the most recent compilation is in 2005. And the report was recently released on that. I just happen to have it here. It's Circular 1344, Estimated Use of Water in the United States in 2005.
Someone asked, I'm not sure what the number was, but how long does it take to do each of the regional aquifer studies?
They approximately take 4 years each to do, some a little more, some a little less. And, that's probably a simple answer because there's a lot that goes into it. There's very specific prescribed products, as I mentioned, that must be developed on the way, but typically 4 years.
So then overall, what's the timeline for completion of the study, and is there a schedule for the priority basins?
I showed an image up there, and I purposely, I guess, chose not to. Looking back, I probably should have shown the starting and end date for those we're working on now. And we have the 30 others that would make up 94% of the water use for the U.S. And there are various criteria that go into the selection of which is the next studies. The various availability issues would, sort of rise a particular aquifer unit in our rankings. Also, the ability to leverage resources and collaborate with others is important. We want to take advantage of synergy that might be available in an area. and we want to make sure we have the proper mix of talent to be able to do those studies.
So which one is the highest priority one being studied, and why was that decided upon?
Okay, I'm flipping back to that very image. This is where we're studying now, and as a matter of fact, I had another showing of what studies have been done. Studies that are completed are the Central Valley, the Denver Basin, and the Southeast Coastal Plain. Currently, projects underway are the Floridan, the North Atlantic Coastal Plain, the High Plains, the Columbia Plateau, and the Basin and Range. And they're staggered such that we start one new study every year, so every year one study completes. So we have approximately 4 studies going on at any one time, various stages of completion.
So what do you feel is the best way to make policy decisions at this point in time if we don't have for sure the measurements we need to make good decisions, or how do you feel about that a little bit?
Well, obviously I've just given a presentation on how to acquire the information necessary to make these decisions, and I'm talking about effective management. And unfortunately, I think what happens is people try to use the best amount of information available to make the decisions they have to make. And what I would like to do is try to provide the information that they need to make an effective decision with regard to management and the policies.
Another question, do you know of any successful models that have effectively integrated groundwater into watershed management? Watershed management often focuses on surface water but ignores groundwater.
Right. Yeah, there are examples. I'll just go back to the Central Valley model. That was a ModFlow 2005 model with what we call the farm process that was used in there. And that had the ability to link surface water deliveries and recharge, discharge, evapotranspiration, crop water demand, all those things in the near surface with the groundwater system. So you have the ability to see water move between the surface water and groundwater, in in this case, in their simulation was a yearly basis. There are models that can do this, but I want to caution you that these are regional models, large-scale models, so they are somewhat limited. But there is a capability, once we develop this regional context, to do LGR, which is local grid refinement, where we're able to look at a smaller scale, and then we can look at the effects of, perhaps, as an example, what we did in the Lake Michigan Basin, individual wells on stream flow, and the reason being there, the interest was maintaining certain ecological flows.
Were the groundwater availability studies initiated at the request of Congress? Was one of the questions.
Yes, this effort was started in 2002, and we had a pilot study in 2005. The Lake Michigan Basin was that pilot to look at methodologies and techniques for assessing groundwater availability. And the combination of that Congress request made us develop this plan and strategy as I showed, and these are an outgrowth of that. And that 2008 report on groundwater availability in the United States is a roadmap for how we would accomplish national assessment.
Final question is, can treated wastewater be used to recharge aquifers? Has this ever been done?
Absolutely. I think on the West Coast it's done to a large degree in the arid and semi-arid areas because there's a necessity to do that. And artificial recharge and infiltration ponds, and there are other ways of returning water to the groundwater system. There is a lag time associated with those things, and that must be sort of computed with regard to availability. But there are other and varied mechanisms to enhance recharge in the groundwater system.
All right. Well, Kevin, I appreciate your time with us today, and we want to thank everyone for attending today's webinar. An on-demand version of this webinar with Kevin will be available at our webinar button. But as a registrant for this webinar as well, I'll be sending out a coupon code to access it for free as well. If you don't receive that, be sure to email me at webinar@groundwater.org, and I'll get that information to you. All of our 2009 webinars are available for free on demand too. We had some pretty interesting ones last year. If you'd like more information about any other Groundwater Foundation programs, you can visit our website at groundwater.org. We're also available on Facebook and Twitter and LinkedIn. And as Kevin said, Kevin's email is kdennehy@usgs.gov, and if you want to reach out to him with any more questions. So that concludes today's webinar. I hope you all have a great day.